Hi, my name is Marissa Miller. I am part of the Prestige Worldwide project team. My teammates are Michael and Mohammed, Julia, and Jacob. We were tasked by Knitline Chemicals to create a xylene plant. Knitline Chemicals has asked us to create this plant at an existing plant in the Gulf Coast. This plant will take 3 years to build and have a startup date in 2023. Toluene will be our major reactant, and it will come into the process with a flow rate of 20,900 pounds per hour. This plant will have an operating time of 8,400 hours per year, and the plant will have a life expectancy of 15 years. We have 3 reactions happening at this plant. The major reaction is toluene disproportionation. This reaction produces xylene and benzene. In the mixed xylene that's produced, we have paraxylene, orthoxylene, and metaxylene, where our major product will be paraxylene. We also have a side reaction called toluene hydrodealkylation, which also produces benzene that we'll sell, and a second side reaction that is xylene disproportionation. As you can see here, we have 8 specs that we wanted to meet when we were designing the plan. In the green are the specifications that we did meet, and in the red are the ones that we didn't. The first 6 are soft specs, and the last 2 are hard specs. The 3 that we didn't meet were all soft specs, so that was good. This could lead to not enough product being made, coking of the catalyst, chemicals being released into the environment, and reverse equilibrium reaction occurring. And again, we did meet our 2 hard specs, which was good. And now Julia will discuss the block flow diagram.
So I'm going to give a quick rundown of our block flow diagram. In total, we have 7 major operation units. 2 are recycle streams and 3 are our product streams. So our first major unit would be our Parex unit, and it is an absorption unit used to separate our paraxylene from our other 2 isomers, meta and orthoxylene. This process is a trademark process and license, and we were tasked in the beginning of the project to use this to separate those mixed isomers. Next, we have our hydrogen pressure swing absorption unit, which is used to purify our light products coming out of our flash unit, which would be our hydrogen, which is used for our recycle stream, which is thrown back into the reactor, as well as our methane, which we are selling off as fuel. Next, we have our 3 distillation columns, our first one being our benzene, and as I mentioned, benzene is being used as one of our products, and then we also have a benzene purge coming off of that column. Our next tower would be our toluene tower, and that top product produces a recycle stream that is used in our reactor. And then our third column would be our trimethylbenzene. And then lastly, we have our vapor-liquid flash separation unit. This unit uses vapor-liquid equilibrium to separate our light products, which are hydrogen and methane, and then send our heavier products down into the rest of our distillation towers. And as I've mentioned already, we do have hydrogen recycle streams and our toluene recycle streams. As Marissa mentioned, some of our specs were met for our recycle streams, whereas others, such as toluene, were not met, and we had a much greater weight percent of toluene heading back into the reactor than we hoped for. And then again, just to emphasize our 3 major product streams, benzene, our mixed isomers, which we were able to sell our mixed isomers because they did match that 99.99% purity that was required. And then we also have our paraxylene, which is sold as our most expensive product and our main product. And just to give an overview of our mass balance, we were within the required tolerance of 99.99%. As you guys can see in the beginning of the block flow diagram, A01 and A02, those are our inlet streams. That would be our fresh hydrogen stream, as well as our fresh toluene feed. And then now highlighted would be all of our outlet streams, as I mentioned before. Those would be our products, and then we also have 2 separate fuel streams as well as a purge here. And just to highlight again, our required tolerance was 99.99, and what we ended up getting was actually 99.998% tolerance. Therefore, our mass did balance. And I'm going to hand it off to Mike next to talk a little bit about our reactor.
Thanks, Julia. One of the most important pieces of equipment in our plant is our reactor for the plant, which produces our mixed xylenes and also our benzene products. We can then separate the mixed xylenes into paraxylene and other xylene isomers to sell. So this reactor is a very important part of our model. So we modeled the reactor using research and development data that was provided to us by the Knitline Chemicals Company. You can see here that I plotted the toluene conversion for R&D data and also the full-scale model at a range of temperatures. We were able to operate our model in Aspen Plus from 560 to 660 degrees, which was a 100-degree range. We actually operate our full-scale reactor at 650 degrees. So I highlighted here that the full-scale model is a slight overprediction of toluene conversion versus the research and development data. I also plotted the paraxylene selectivity of our full-scale model in blue versus the R&D data, which is shown in orange. Like I mentioned, we're still running from that 560 to 660 degree temperature range, and our model is operating at 650 degrees Fahrenheit. You can see here that the paraxylene selectivity is a much closer fit for the full scale versus the R&D model. There's only about a 2% difference there. And so I highlight here for you the variables that we're looking to control: the toluene conversion, paraxylene selectivity, and benzene selectivity. So the reaction kinetics were optimized to help match these versus the R&D data in our full-scale model. As I mentioned, there is a slight overprediction of toluene conversion, about a 17% overprediction. We were still happy with that as a project team. We were targeting about a 20% difference between the R&D and the full-scale model. But as you can see, the paraxylene selectivity and benzene selectivities are only a slight underprediction, so we are very happy with those as a project team. I'll now pass it over to Jacob Socha to discuss some of our plant economics.
Thanks, Mike. Right, so our plant currently has the capacity to produce 62 million pounds of paraxylene annually and generates a total annual revenue of $64.92 million a year. And let me break down that revenue for you right here. So we have over here 85% of that revenue is generated by the sale of benzene and paraxylene. And of that 85%, these two make up pretty much 50-50, right? They're split evenly of that 85%. The other revenue that our plant generates is from our sale of side products, right? And the majority of that is from our mixed xylene stream, as you can see here. That mixed xylene stream makes up 90% of that remaining 15% of the total revenue that we have, right? And then last, you can see the steam generated and fuel credits, and that's the last piece of our total plant revenue. And those make up roughly 1% of our total plant revenue, so not a very significant portion, but still help to contribute. Next, I'll break down the equipment, or the total capital cost for the plant, right? So the total capital cost for our plant, including IBL and OBL equipment, was roughly $80 million, right? And the majority of this was from the total contractor cost, inner battery limit cost, right? And that makes up about 55%, as you can see there. That is by far the largest portion of all of our expenditures. So I'll break that down right here. So that includes, that IBL includes all of our unit operations. And the most expensive is by far the PERIC system, right? And this is pretty much the cornerstone of our plant. This is what enables us to separate our P-xylene from our mixed xylenes and actually produce two of our big revenue producing streams, right? And that PERIC system is roughly 26% of our total IBL cost, so a very significant portion. Right, so now I'm going to break down the ongoing cost to the plant. As you can see here, the most expensive ongoing cost of the plant was by far and away the raw materials cost. It constitutes 81% of our raw material cost to our plant. And of that 81%, over 90% is comprised of toluene. As you can see here from that little table that popped up, $45 million per year is spent on toluene, which is a very significant cost to the plant, right? And then the least impactful ongoing costs to the plant were our fixed costs. And of these fixed costs, labor and taxes make up the most of that. Labor and taxes contribute roughly 3% each to the total ongoing cost of the plant. And lastly, we have our utility costs, and that's highlighted right there. And next, I'll break those down in this pie chart right here. So of our utility costs, most expensive one was our power cost. And this is because we have a few compressors that are big energy users, but also because the plant employs so many pumps, right? Virtually every stream has a pump in order to send the stream where it needs to go. So that's why our power cost is so high. That power cost is highlighted right there. And now I'll turn it over to Mike.
Thanks, Jacob. After all of our cost analysis was conducted, the team made a cash flow model for the plant where an ATROR after-tax rate of return could be calculated, and also our cumulative net present value of the plant. So you can see here that I have plotted the after-tax cash flow of the plant versus the year of the plant that we're running. So you can see that we're only in the green, which is a positive after-tax cash flow, in the second 2 years of operation. So we start by ramping up at 40% capacity, then 75% capacity, then 100% capacity for the plant. So in 2024, we're running at about 75% capacity. 2025 is about 100% capacity. So you can see that those are the only 2 years that we are operating in the green for after-tax cash flow. Therefore, our cash flow is negative for the plant in all other places. So our ATROR target of 15% was very difficult to reach, and we were unable to reach it because basically our ongoing costs were outweighing our revenues that we were gaining from our products. Based on that, the cumulative present worth over all the years of the plant was plotted here, and you can see that at the end of our plant, which our wrap-up is in 2038, our net present value is about negative $66.4 million. So you can see that based on the graph before of after-tax cash flow, we do have a slight increase in our cumulative present worth in 2024 and 2025. However, it's a steadily decreasing trend after that due to the negative cash flow. So we conducted 4 sensitivity analyses on the plant to basically figure out how different changing variables would affect the economics of the plant. Here we have looked at and researched historical toluene and xylene prices, particularly from 2018. So we basically took data points from every single month that year and also the minima and maxima. You can see in the red, that's the range of prices of toluene, and green is the range of prices of xylenes. So by taking all of these data points, we were able to process a linear regression and get a standard deviation of the historical data, and then apply that to our particular process. So you can see here in the red we have the toluene prices plotted. The net present value of the plant is on the y-axis, and the price of the either input or product is on the x-axis. So red is toluene, blue is paraxylene, and we have circled here the provided prices for our plant of toluene and paraxylene product. As I mentioned before, we were able to do a linear regression on the historical prices, and we basically analyzed those 2 standard deviations away from our particular prices that we were provided for the plant. So you can see those highlighted in yellow here. I'd like to highlight that the toluene prices have a much greater effect on the net present worth of the plant. You can see this by the greater slope of the red line versus the blue line. It's actually about a 3 times greater effect of the toluene versus the paraxylene on the plant net present worth. I'll now turn it over to Mohammed to discuss some of our alternate designs that we evaluated.
Thank you, Michael. As mentioned earlier, in our base case design, we have a benzene distillation column with partial vapor condenser. The purge stream, which is the benzene vapor coming out from the top of the column, was sent to the fill system. By adding an additional distillation column to purify the benzene vapor, the benzene vapor will obtain more of the benzene product. With the additional column, we will have a capital cost due to the condenser and reboiler of the distillation column. The additional revenue by the benzene product will undergo economic evaluation. The difference of net present value between before and after the alternate design was calculated and to be $18 million. This shows a significant improvement on this first alternate design. For the second alternate design, we decided to sell the bottom stream of the pressure swing absorption. In our original base case, the bottom stream of pressure swing absorption was burned off as fuel. Was burned off as a waste. With the additional of heat exchanger, we will have an extra additional capital and operating cost. This is because the heat exchanger was used to heat up the vapor liquid mixture to become only vapor stream. The additional revenue from the stream coming out at 793 pounds per hour. The difference of net present value between the second alternate design and the base case is $2.5 million. Next, I will hand over to Mike.
Thank you, Mohammed. So based on all the alternate designs and all the economic evaluations we did on our base case, we have a couple of suggested recommendations that we have wrapping up this project. So on our base case design, our trimethylbenzene stream coming off the bottom of the xylene trimethylbenzene tower is about a 99.8% purity. If we get this up to the 99.9% purity required to sell it, we could add an additional $300,000 of revenue per year to the plant. As Mohammed mentioned, we also had two alternate designs that we investigated as a design team. So the first one was adding that additional benzene column to purify the vapor benzene purge stream coming off of that partial condenser. That adds an incredible amount of revenue to our plant, increasing our net present value from about negative $66 million to about negative $50 million, which is a significant improvement of about $16 million in net present value. Also, the second alternate design, like Mohammed mentioned, was the pressure swing adsorption. Originally off the bottom of that column we had a vapor-liquid mixture. If we add a heat exchanger, we could then make that a purely vapor stream and send that to our fuel system to sell. Both of those alternate designs combined adds an additional $5 million of revenue per year to our plant. Also, I'd like to mention that our flow rate, which was 20,900 pounds per hour, could be increased. If this flow rate is increased, we would increase the capacity of our plant. However, the capital required to reach our purities would not increase linearly with that, so we would have an additional revenue increase that was greater than our capital increase. So we would suggest that increasing our flow rate would also help increase the production of our plant and increase the economic feasibility of the plant. Overall, I'd just like to recommend that the design be postponed for now until these economic issues can be addressed and different alternate designs can be implemented to the design. Thank you for your time.